This playlist will collect together and organize the individual component modules, which together will comprise our second lecture on philosophical theories of mental representation. In this lecture, we're going to cover the remaining two theories, the theory of gnomic covariation and the functional role semantics account. When we look at gnomic covariation, we will look at some important plausible instances of gnomic covariation in cognitive science. Then we'll look at some of the advantages that advocates of gnomic covariation claim for the theory. And finally, we'll consider some of the problems or challenges that the theory faces. Once we've completed our discussion of gnomic covariation, we'll turn our attention to the third and last theory that we'll consider, functional role semantics. We'll begin by talking about functional role semantics, distinguishing between the wide version and the narrow version of the view. We'll discuss some of the advantages that advocates of functional role semantics claim for the theory, and then we'll consider some of the problems that critics bring up for the theory. So let's switch now and turn our attention then to gnomic covariation. Gnomic covariation, like functional role semantics, is a use theory. It understands mental representation in terms of how the system uses that mental state, what roles that it plays. And specifically, gnomic covariation holds that mental states represent an object or a property, an event, or relation in virtue of the fact that occurrences of that particular mental state reliably covary with occurrences of that particular object, property, or event. So for example, if there's a triangle and we were to take our philosophical fMRI and look into Homer's brain, it would covary with his tokening of the state, call it S sub t. And if it did, that would in fact constitute the representation of triangles. So a state ST represents a triangle if and only if the system tokens that state when, only when, and because of triangles. Now, you might be tempted to suppose that this theory looks cartoonish, maybe because I'm depicting it with a cartoon. However, there are many examples of plausible and important instances of researchers identifying the representational content or capacity of parts of the brain, specifically of sensory systems, by doing just this. In psychophysics, using the relationship between an external stimulus and the activation patterns of the particular part of the brain that you're looking at. So for instance, the sensitivity curve, the selective sensitivity of each of the three cones as well as the rod in the retina in the back of your eye, those were all discovered by doing single cell recordings on homolog cells in, well, mostly toads, but in some in cats as well. So that they were looking to see what kind of light activated these cells, what these cells were sensitive to. And because of that gnomic correlation, they made that inference to the representational content of the activation patterns of these cells. Now, this seems abstract and hard to get a hold of, so I'm going to show you a brief version of a video from the 1960s research on the striatal visual cortex by Hubel and Wiesel, in which they do exactly the same thing, but for higher level features, edges at orientations. Indeed, covariation relationships between stimuli and neural response have been used to hypothesize contents for individual cells, but they've also been used to hypothesize the contents and to explore the extent of whole systems for processing. This image from Ming et al. Depicts the core face recognition system in the brain. This face recognition system was discovered in part because people stumbled upon a correlation between faces and activation in the fusiform gyrus. Using that correlation and functional magnetic resonance imaging, researchers were eventually able to trace out an entire system, a core network that they hypothesized is responsible for processing information about faces.